Good morning. This is the third in a series of videos reviewing acid-base chemistry in support of the content that we will be discussing in aquatic chemistry. In this problem, we're going to be working with weak acids and weak bases, but the pH of the solution is going to be known, and this is typical of a problem where we want to understand the distribution of acids and bases in a lake or stream environment where we can take a sample, put a pH meter into that environment, and measure the pH. So we say that pH is a master variable because pH is known. It's known because we can measure it. All right, so we're going to start with a chemical equilibria. HA, this is going to be our weak acid. It's going to go to H plus and A minus. That's going to be our conjugate base. Like the last video, we have an equilibrium expression. Doesn't matter how you start the problem. You have an acid-base equilibria, you have the same equilibria expression. Ka equals conjugate base times H plus divided by the concentration of weak acid. We also have conservation of mass. The total concentration, THA, is the sum of all the weak acid and all the conjugate base. And so we would need to know that. So in this problem, let's assume it's 0.01 molar. So it would be measured. And the last variable is the H plus concentration. Since pH is often measured, and in this case pH is measured, we also can compute the H plus concentration. So if you look, and we'll switch to red here, I have still three unknowns, HA, H plus, and A minus. I have three equations, 1, 2, and 3, and the pH will be measured, and the total THA, total weak acid and base, the sum of those two is given, again, 0.01 molar. So we set up the problem. Now we're going to do a bit of algebra, but in our algebra in this case, we're not going to solve for H plus because we know it. What we're going to do is solve for concentration of HA or the concentration of A minus. So in the homework assignment you're going to have, I'm going to ask you to solve for the concentration of the ammonium ion, NH4 plus, and the concentration of ammonia, NH3 aqueous, in a water sample that has a known pH. Okay, so we'll do our algebra. Again, we're going to reorganize our conservation of mass equation to solve for HA. I'm also going to recognize that I can reorganize the equilibrium expression to solve for A minus. And then I'm going to build a ratio. It's a fraction, HA over total A. So it's the fraction of the total weak acid that's in the acid form. So notice that's just simply HA over the sum HA plus A minus. Now this fraction turns out to be really helpful because if I know the fraction of NH4 in a sample, let's say it's 50%, then I know that the NH4 concentration is 0.5 times its total concentration of 0.01, so it's 0.005. So if I know the fraction of any of the acid-base forms, and I know the total concentration, the whole system is defined. All right, so keep going with my calculation. Here's my fraction. I'm just doing a little algebra, substituting in for A minus. So, this term right here is just A minus. Okay, get rid of the HA, which is in every term, reorganize, and I get this really neat, clean expression that the fraction of acid in a sample is H plus over H plus plus Ka. So notice the pattern that's going to emerge here. And I'm looking at the acid form. I've got H plus in the numerator, and my denominator is H plus plus Ka. So this is the fraction of total acid. And, and we call that alpha HA. Okay, so it's the fraction of total acid and base in the acidic form, right? Because it's H plus over THA. We call that alpha HA. So that's what I've done. I've just rewritten that here. Okay, so the concentration of HA is the fraction times the total. I said that above. So if we knew that this was 0.01 and this was 0.5, this would be 0.005. Okay. By doing a bit more algebra, you can also show that the fraction of the base is Ka over H plus over THA. So I'll leave it to you to work out that algebra. But notice again the pattern. The numerator in this case is Ka instead of H plus, but my denominator, which is the sum, is H plus plus Ka. We're going to use this pattern strategically as we move from simple monoprotic acids, where only one proton comes off, to polyprotic acids. And the example we're going to do a lot, the problem we're going to solve a lot, is the carbonate system, because it plays such an important role in controlling the acid-base chemistry of most natural waters. So following up, the A minus concentration is going to be equal to the total concentration times alpha A minus. And so, we can do 0.01. And let's face it, if it's half acid, it's also half base, 0.05. Now, the last thing I should say is the 0.5 in both of these is calculated, and so you'd have to plug in the H plus into these expressions. Ka is known to calculate that fraction. So that will be part of your first homework assignment, will be to calculate the fraction of NH4 plus and NH3 in a sample with known total ammonia.